you can start. Okay.
Are you going to introduce me or should I just start?
No, I'm going to introduce you. We're starting.
Okay, sorry.
The live stream. Just a moment. Can I start? Yeah. Okay, so hello everyone. Today we restart our 2024 first semester seminar series with Professor Rosemary Wyse from the Johns Hopkins University in the United States. Rosie obtained her PhD at the University of Cambridge in the UK in 1983. She then held postdoc positions in Princeton, Berkeley, and Space Telescope before starting as an assistant professor in 1988 at Johns Hopkins. She has received several prizes, and in 2017, she became an elected member of the American Physical Society and a legacy fellow of the American Astronomical Society in 2020. Rosie has spent several scientific visiting periods around the world, with the latest one being in Japan. I probably forgot to mention many of Rosie's achievements, but today she has kindly agreed to present us her seminar entitled Ultra Faint Dwarf Galaxies, What They Are and Why We Should Care. Thank you so much, Rosie. You may start when you're ready.
Right, thank you for inviting me to give this seminar. I would, of course, much prefer to be there in person, and hopefully one day I will manage to spend one of my visits with you in Brazil. So most of my career I have devoted to galaxy formation and evolution across the range of galaxy masses using both theory and observational techniques. But recently I've become fascinated with the smallest galaxies, and I thought I would share with you some of our results, some of the open questions, and also what we hope to do with the prime focus spectrograph on Subaru. And perhaps some of you will get more involved with that. So I understand that among you listening, we have undergraduates and graduate students. So I will give an overview, and I'll be reminding you of results from stellar evolution and other physical processes that are important to how galaxies evolve. So I hope that those of you who are experts in the field will be patient with me at that point. So just to get us going, I'll tell you what I'm going to tell you, and then I'll tell you it. So the first important question, the part of my title, what are ultra-faint dwarf galaxies? Well, observationally, they're extremely low luminosity systems. They tend to be satellite galaxies of larger galaxies. I've put a question mark there because just recently there have been two new discoveries of extremely low luminosity systems that we think are galaxies that are actually between the Milky Way and M31, and it's not clear that they're in orbit about either large galaxy. But the vast majority of ultra-faint dwarf galaxies are satellites of other larger systems. They seem to contain just stars, at least observationally. There's little or no gas. The stars that they do contain, there's very few, and they're quite far apart, so they're extremely low surface brightness on the sky. They've been detected so far by a slight overdensity in star counts, basically. So they appear like star clusters, but with much larger radii than would be typical for a star cluster. So what's the importance of these very small systems? Well, the first aspect of them that I think sets them apart is that even though they have very low luminosity, they contain much more mass than is observed in the stars. And indeed, they're among the most apparently dark matter dominated systems in the universe. They're very dark matter dominated. They have a very low baryon content, just the few stars. So that means that they have a low enough baryon content that it basically hasn't disturbed the distribution of dark matter. And we'll see later that in more luminous galaxies, the baryons can actually change the distribution of dark matter. So that means with these ultra-faint dwarf galaxies, if we can determine the distribution with radius of the dark matter, that's telling us what the dark matter itself wants to form as the density distribution. That's what I've referred to as the primordial dark matter distribution. And that depends on what the dark matter is. So that's very important. The stars that are in the ultra-faint dwarf galaxies all seem to be extremely old. That means they formed at very large look-back times. So when they formed, it was very early on in the evolution of the universe. So they're probes of the physical conditions at high redshift. They're very chemically unevolved, and they probably all formed together in the dwarf galaxy. And they're unique probes of stellar nucleosynthesis at high redshift. And that includes the origins of very heavy elements, those beyond the iron peak in the curve of binding energy per unit nucleon. We live in a large galaxy. In our current paradigm of cluster of galaxy formation, predicated on the dark matter being cold dark matter, we start with small systems which merge to form larger systems, and these ultra-faint dwarf galaxies are plausibly examples of building blocks of larger galaxies. So for all these reasons, you should care. So now let's explore in more detail some of these aspects of dwarf galaxies. But first, for context, let's consider our galaxy, which is a typical large disk galaxy. And the field of study of our Milky Way, commonly referred to as galactic archaeology, also near field cosmology, to reflect this idea that by looking locally at old stars, we can constrain star formation at high redshift at cosmological look-back times. That field has really been transformed by the ESA satellite, astrometric satellite Gaia. And here's just a view of more than 1 billion stars in our galaxy. And you can see most of them are in the disk. We have the bulge in the center of the image here, in the center of the galaxy. This galaxy, the stars and dust are concentrated to the disk. And let me just point out to you here there's a tiny globular star cluster. So there are stars very far from the disk. We have a globular cluster here, just stars. We also have two satellite galaxies, the Large and Small Magellanic Clouds. So galaxies have star clusters far from the center, and they have satellite galaxies far from the center. Of course, although this globular star cluster and the galaxies are together on the sky, they're at different distances. And one of the important aspects of Gaia satellite was that it measured geometric distances for millions of stars in our galaxy and beyond. So we have a cartoon of the Milky Way galaxy. We have the bulge, older stars, the thick disk, which I worked on a lot in the 80s and 90s, establishing those stars were old. The thin disk, where stars are forming, younger stars, including up to zero, since stars are forming there now. And we have this halo, the oldest stars, where we find these globular star clusters. So to set some scale here, the sun is about 8 kiloparsecs from the galactic center. The stellar disk extends about 30 kiloparsecs from the galactic center. Thin disk stars are on close to circular orbits about the center, high angular momentum. Halo stars, including the globular clusters, and in general, including satellite galaxies, are on far from circular orbits, which we refer to as hot kinematics. So I'm going to go through why we think ultra-faint systems could be galaxies. So let's just think about what is the definition of a galaxy. It's a vast assembly we have of stars, gas, dust, and dark matter, and they're all held together by gravity. The gravity is dominated by the dark matter in general. In the disk of our galaxy and towards the center of our galaxy, the baryons, the stars, are actually very important contributors. But overall, the gravitational potential, the gravitational field is dominated by the dark matter. The relative fractions of stars and dark matter, stars to dust, etc., varies from galaxy to galaxy. And nowadays, there are many more low-mass galaxies than high-mass galaxies. And galaxies clustered together. We have the Milky Way and its satellites. We have the local group, which is basically the Milky Way, its satellites, plus M31 and its satellites, and all the way up to clusters of galaxies. There's gravitationally bound systems on a variety of scales. And I mentioned stars are forming today, and that the average age of stars varies through galaxies. And we'd like to know what makes stars form, where they formed, what are the properties of stars, how did star formation differ, if it did, at early times than it does now. To probe early times, we take advantage of the fact that even though the most massive stars live for only a few millions of years, a star of order the mass of the sun has a lifetime that's much longer, of order 10 billion years, which is of order the age of the universe. So if a star of the same mass of the sun or below formed 10 billion years ago, it's still around now. So old stars nearby trace conditions of high redshift. 10 billion years is about 10 billion years ago is about a redshift of 2. And the way star formation, I would say, operates, or the way stars form, there are many more low mass stars in a burst of star formation than high mass stars. So we have many ancient low mass stars nearby that we can study. So I mentioned satellite galaxies of the Milky Way. I pointed out too the Large and Small Magellanic Clouds. Those are quite massive for satellites and have a lot of gas and ongoing star formation. They're actually not typical satellites. A more typical satellite is like this one here, called Leo 1, the first satellite found in the line of sight where the Leo constellation. This is we refer to as a dwarf spheroidal, dwarf meaning low luminosity, spheroidal meaning it looks sort of spherical on the sky. It consists observationally of stars and no gas. This one is at a distance from the center of the galaxy of about 250 kiloparsecs. So almost 10 times the extent of the disk of the galaxy. We do see dwarf galaxies more nearby. In fact, we see one inside the Milky Way, the Sagittarius dwarf spheroidal. It's actually seen here an outline of where in 1997 we had traced the outline of the Sagittarius dwarf. It's on the other side of the galactic center. It's shown here projected against the bulge of the galaxy, but it's actually on the other side. And it's on an orbit coming up from having done a circuit around the center of the galaxy. It's coming up, it's being stretched out due to tides, the gradients of the gravitational field of our galaxy. And this is an ongoing merger of a satellite galaxy, one of the building blocks of bigger galaxies, into our galaxy. Stars will be lost from it and it will be assimilated into our galaxy. This dwarf galaxy was discovered by Roddy Ibata and Jerry Gilmore during their survey of the central bulge of our galaxy. They had spectroscopic fields around here, some crossing this area of sky. Mike Irwin then mapped out the extent of a system that matched the properties of the moving group that they found as part of their spectroscopic survey of the bulge. They found stars that all seemed to be moving together, but were not moving similarly to most of the other stars at the center. And they then found also the colors of the stars were different from the bulk of the stars in the center. So satellite dwarf galaxies can be found from their distinct color magnitude diagram and then confirmed as galaxies by getting kinematics. We now have much better wide field imaging surveys, and we can see that the Sagittarius dwarf is being tidally disrupted by the Milky Way, and debris from it are seen across the sky. This is a figure taken from Belukharov et al. Of star counts in the Sloan Digital Sky Survey. This is a wide area across the sky close to the well, starting at the equator, we have declination, 60 degrees of declination from 0 up, and angle on the sky. Again, we have about 100 degrees here. What I hope you can see, the stars here are faint stars. This is the apparent magnitude in the R band, and they're colored, they're bluish stars, and they're color coded in this plot by their apparent distance. They're color coded by their apparent magnitude. The stars are all similar main sequence stars, dwarf stars, so color coding by apparent magnitudes, color coding by distance. What you can see is blue is nearby. There's a blue swath here, green, intermediate distance, about 20 kiloparsecs away, again a swath, all at the same distance, and then redder being more distant again. So it's far from uniform on the sky, showing us debris from satellite systems that are being tidally disrupted. We have the orphan stream, streams from the Sagittarius dwarf, and what was referred to as the monoceros stream. So this image was referred to as the field of streams. The monoceros stream was thought to be, it's in the anti-center direction. This is towards the outer disk of our galaxy, and it was thought to be a disrupted satellite. So the question was, is it a satellite, or is this structure in the disk? And we now have got better data, spectroscopic data, and this is structure in the outer disk. What you can see is written here, the outer halo is dominated by spatial overdensities that are dominated by the Sagittarius dwarf. It's about equal mass in stars from the Sagittarius as there is in the smooth halo, and a lot of structure towards the outer part of the disk is actually internal to the disk. A lot of work from Gaia. But let me turn to the main topic of my talk. This is not just the field of streams, it's the field of streams and dots. There is a little red dot here. That's stars from the Bootes, dwarf spheroidal, ultra faint dwarf, we now know, is another little dot here. These are stars spatially coincident in distance and also on the sky. These are clusters of stars. Down here, there's also a dot with a stream. This is Palomar 5, a globular cluster in our galaxy. So these new systems, these ultra-faint dwarfs that were first discovered due to the uniform photometry that Vasily Bulukarov created for the Sloan Digital Sky Survey, they overlap in luminosity between galaxies and star clusters. This is a plot of absolute brightness of a system versus the half-light radius, a measure of the concentration, the size of the object. The left-hand side are star clusters. I mentioned a galaxy has dark matter. Star clusters, as far as we know, have no dark matter. They're held together by just the gravity of the stars. The right-hand side, we have dwarf galaxies. The brighter systems were known to have dark matter. Before the discovery of so most star clusters are fainter than about 10 to the 5 times the luminosity of the sun. And before the discovery of these very faint systems, there was a gap in radius between star clusters with no dark matter and dwarf galaxies, and the star cluster range of luminosities extended much fainter than the dwarf galaxies. But these new systems extended the overlap between star clusters and dwarf galaxies in luminosity. There's no longer a distinction, and there's also no longer a distinction in size. So they're very strange. How do we know that these systems are galaxies? Well, we expect to have lots of very faint galaxies if we have a system where dark matter that controls the gravitational field is cold. Then I have very small systems forming first, and they merge to form large systems, just shown here in two snapshots, very early times. Over-dense regions, self-gravitating regions of dark matter are labeled by red here, the most dense systems at early times likely to form stars, clusters together to now. And you can see lots of, the gray is dark matter only. Again, the red is where we think stars likely formed. We have luminous dwarf galaxies, many of them predicted, and also many dark systems. And this led to what was referred to as the missing satellite problem. There are many more predicted, even luminous small dark matter halos than observed satellites. And there's just an example here of predicted. This is dark halos, but many of these should have stars and the dwarf spheroidals. Of course, as we have better and better surveys, better techniques to find satellite systems, we're finding more of them. Here's just a figure from Simon and Geha in 21. That was this back here was 99, to show you the progress that we've made since Sloan, and then Pan-STARRS, Dark Energy Survey, and Hyper Supreme Cam. We're finding more and more dwarf satellites, but we're still not at the predicted distribution and luminosity function predicted by cold dark matter. But of course, we're all looking forward to the Roman satellite and the Rubin satellite LSST survey, expected to find many more dwarfs. One of the new dwarfs that was discovered by the Dark Energy Survey, just shown here, this is a snapshot taken from the Dark Energy Survey pages at Fermilab. This is an area of sky, quite a few stars here, but if you remove the foreground stars of the Milky Way, there's a few stars visible here, and that's the galaxy called Reticulum 2 that I'll be returning to later. It's particularly interesting because this could be a satellite galaxy of the Magellanic Clouds, the Large Magellanic Cloud, which itself is a satellite galaxy of the Milky Way. So again, we have hierarchical clustering satellites of satellites. And of course, we'd like to before we leave, we'd like to know, was star formation, chemical evolution, etc., any different if you're a satellite of a small galaxy or a satellite of a large galaxy? I'm going to focus most on Bootes 1 for two reasons. It's relatively nearby and it's relatively bright as far as ultra-faint satellite galaxies go. Its luminosity is close to the kind of working definition of ultra-faint, which is less faint than 10 to the 5 solar luminosities. Its distance is actually about 60 kiloparsecs. Here's an update of that plot I showed of absolute magnitude or luminosity versus half-light radius from Josh Simon's 2019 review. It's actually labeled, notice, by these lines are surface brightness, showing you the equivalent surface brightness in these very faint dwarf galaxies is a tiny fraction of the night sky. Again, these are globular clusters, and these are candidate galaxies and confirmed and suspected galaxies. And we'll discuss, how do I know things are dwarfs? Bootes 1 is this one. And the one we just talked about, Reticulum 2, is this one down here. So significantly fainter and a bit lower surface brightness than Bootes 1. Observationally, Bootes 1, I can get the color magnitude diagram. I can identify a main sequence turn off, and a giant branch. I can fit isochrones to this. This is the Okamoto et al.'s Supreme Cam with Subaru data reaching fainter than the left, which is CFHT data from Belukharov et al. And the isochrones that fit are metal poor, 1/300 times the metallicity of the sun, and very old, fitting very well the main sequence turn off, giant branch, even the horizontal branch. On the left here also shows a very good fit. But what's being shown here is the ridge line of an old metal poor globular cluster. So just based on the color magnitude diagram, it just appears the same as a globular cluster. How can we figure out whether it's a galaxy or not? One hint comes from the chemical abundances of the stars. So let's just remind ourselves where elements come from. The early universe just gives us basically hydrogen and helium. Everything else comes from stars, and stars create metals in their centers to get energy out by fusion. Then they radiate that energy. That's why they're shining. When they die, they generally explode, and that puts back metals so that the next generation to form from gas forms from material that's been enriched. Then we have another cycle of star formation and death, and the metallicity increases with time. The sun is about 2% by mass in metals, and of course, everything of which the Earth and us are made of was created in stars. Importantly, stars of different masses create different elements on different timescales. And if I measure elemental abundance patterns of stars in a system, I can get a get constraints on both the stellar mass distribution and the star formation history. So only massive stars are hot enough to reach iron in their centers. But when they get to iron, they can't fuse anymore. And they explode. These are massive stars, about 10 times more massive than the sun. They undergo core collapse. And in this process, the center collapses, the outsides are blown off, gets very hot in the center, and the iron that was created during its lifetime actually gets destroyed. But the outer parts, which have created so-called alpha elements, those created by successive addition of helium, is ejected. So massive stars produce alpha elements. And the iron, a small amount of iron survives, and that's approximately constant, independent of the mass of the star. But the alpha element yield is mass dependent, above about 10 times. So between about 10 times the mass of the sun up to a couple of 100 times the mass of the sun, we get core collapse supernovae. Lower mass stars end their lives as white dwarfs, generally carbon-oxygen white dwarfs. These have a maximum solar mass. If I get enough accretion, or I have mergers of white dwarfs, which are degenerate systems, the pressure balancing gravity isn't an ideal gas pressure, but is degeneracy of electrons, then I can ignite nuclear burning. And if it's degenerate material, I get a thermonuclear runaway. It goes to statistical equilibrium, and I get a lot of iron from white dwarfs exploding as type 1a supernovae. So here's a cartoon of the kind of elemental abundance pattern I would get in a self-enriching star-forming region at early times when I have only core collapse type 2 supernovae. I have a lot of alpha elements, oxygen's an alpha element, and I have sufficient alpha elements that it's enriched in alpha to iron, about 3 times that of the sun. After some time, I form white dwarfs. I start having white dwarf mergers, accretion. I start to get type 1a supernovae. They give me iron, but no alpha element, so I get a turn down. This is against iron, not against time. So the knee is referred to as the knee at which I get iron from type 1a supernovae depends on the star formation rate. So it's a lot of information, even the IMF of the massive stars, because as I mentioned, you get more alpha elements by mass if you have an IMF that's biased towards the most massive stars. What do we see in Bootes 1? This is earlier work I did with John Norris, Jerry Gilmore. You find very low mean enrichment. The iron abundance is about, indeed, from what fitted, the isochrones about 1/300 times the sun's enrichment. Importantly, there's a large spread over 2 orders of magnitude. That implies some self-enrichment. This is very unlike a globular cluster. This is not a star cluster. It is a galaxy. It has very low mean enrichment, very low baryon content, so very plausibly its potential well isn't deep enough to contain the ejecta from supernovae. That ejecta, a lot of it blew out of the galaxy. That would reduce its baryon mass plus its metallicity. So here's iron, showing you the small sample for which we have detailed alpha abundances. But you can see here down to almost -4, -3.7, up to above -2. There is a trend, most seen here in the alpha elements, that's consistent. The value here at the most metal poor star is actually what you expect for a normal massive star IMF. This decline is what you would get with type 1a supernovae producing iron. We know there's a very short range in ages, but it could be 1 billion years. From type 1a supernovae, this is if you have a binary of white dwarfs created at the upper mass limit of stars to form white dwarfs. You can get type 1a supernovae on a few times 10 to the 8 years. And so that seems to have contributed here. So it's self-enriched, it's a galaxy, and it seems to have formed stars with a normal massive star IMF. No change between the mass function at this very early time in a dwarf galaxy than what we see forming stars now in the Milky Way. What about more heavier elements? This is the graph of the binding energy per nucleon. Stars have released energy by fusing up to the iron peak, but we have elements over the iron peak where you get energy out by fission, and we now know that we can create elements beyond the iron peak by actually neutron capture, but then we need a source of neutrons. And we know that, as I just mentioned, the iron core of a massive star is actually photodisintegrated during core collapse. So that gives you a rapid flux of neutrons, happens very quickly, lots of neutrons. Can we see these in dwarf galaxies? So I mentioned reticulum 2, we'll be coming back to it shortly. Alex G, this is not work that I was associated with, but it's really interesting work. Alex G et al. Got spectra of 9 stars in reticulum 2 and found that 7 of them showed very high enhancements in the abundances of barium and europium, elements over the iron peak that have a large contribution to their creation through the R process, rapid neutron capture. It's rapid with respect to beta decay. So these are unstable nuclei you form, and which then decay. The R process is when you add many neutrons before you have beta decay. Most ultra-faint dwarf galaxies don't show this. I mentioned, or at least I should have mentioned, one thing that's important for studying these dwarf galaxies is that plausibly all the stars formed in the system, we think the halo of our galaxy has formed from disrupted systems. And depending on when those disrupted systems were assimilated into the Milky Way, they get very spread out. And it's very hard to identify exactly which star formed in which system. If we have an intact dwarf, it's really quite plausible that all the stars formed together and were enriched in the same event. So this is a plot of barium to hydrogen versus iron, europium to hydrogen versus iron for a whole load of ultra faint dwarfs. Most of them lie below the red points, which is reticulum 2. The pale brown bars here on the y-axis is the expected range of barium and europium you get from a single rare event, a neutron star merger. Dark brown at lower values is what you would get from core collapse supernovae. And that seems to explain the R process elements in most of the dwarfs, but not in reticulum 2. They are consistent with a neutron star merger. Now, this was in 2016. We thought neutron star mergers, like white dwarf mergers that could form type 1a supernovae, neutron star mergers should happen. They might form gamma ray bursts, but we hadn't seen any. But then in 2017, we actually did detect a neutron star merger. Not only that, but this neutron star merger, GW170817, was localized on the sky, and there was an electromagnetic counterpart. You can see the brightening here over several days, plausibly powered by the radioactive decay of the R process element. So everything hanging together, but Alex G. et al. Found the signature in the elemental abundances first. I will speed up a bit. So returning to Bootes 1, we have the chemical abundances of massive stars being consistent with self-enrichment with a normal IMF of massive stars. It's also got a normal low mass IMF, i.e. it's consistent with what we see in the Milky Way. It doesn't vary in the Milky Way from the local disk to the bulge to the halo. It can be fit either by a broken power law or a log normal form. My student who's just about to graduate, Carrie Filion, has been obtaining for Bootes 1, analyzing from the archive for reticulum 2, Segway 1, triangulum 2, and Ursa Major 2, very deep Hubble Space Telescope imaging, doing various analyses, including ABC, MCMC, that's approximate Bayesian calculation with Monte Carlo Markov chain, or comparisons of the Hess diagram, the Bind color magnitude diagram, plus Kolmogorov-Smirnov tests of the luminosity function against given IMF parameter values and binary fraction to figure out what is the single star mass function in these ultra faint dwarf galaxies. It's very important to have comparable ranges of masses in the systems you're studying to be able to do an intercomparison, and also to go faint enough that you have some constraint on where a turnover might be in the mass function. And what we found is that in all these systems, the IMF is consistent with the power law form of the IMF, the Milky Way, and log normal. I put Ursa Major 2 in brackets here because it's only consistent with the broken power law form. There's a slight inconsistency with the log normal form. If you read the paper just about to come out, you'll see that the Ursa Major 2 field has known intermediate redshift galaxy clusters, so we're not 100% confident we removed them all. It's just a plot from the 2024 paper. Bootes 1 was analyzed separately in a 2022 paper. We reanalyzed it in the same way as the 4 other ultra-faint dwarfs. These are grid points in IMF parameters. For instance, the 2 slopes of the broken power law, or the turnover mass and the width of the log normal. The colored points here are IMF parameter values that are not rejected, and the stars are the Milky Way. Upper is just for Bootes 1. Lower combines all the 4 dwarfs, Reticulum 2, Ursa Major 2, Triangulum 2, and Segwe 1 together for the overlap, that they're all consistent with this particular combination of power law slopes or log normal. This does not include Ursa Major 2 here. And what you see is that the colored points are fine and they are consistent with the local values. The local values are, has to be said, at the edge of what's not possible to reject, but are still consistent with this set of dwarf galaxies. So we have a normal massive star IMF and a normal low mass IMF. What else, just in the last few minutes, what else makes a galaxy? Well, it has to have dark matter. We now have enough spectroscopic studies of Bootes 1 to know that the stars don't provide enough gravity to keep it bound. Must be dark matter dominated. Just remind you that you get enclosed mass by having some measure of the range of velocities with which stars are moving. These are non-rotating systems. There's a mass estimator within the half-light radius that's of order given by a factor constant, a few, half-light radius, velocity dispersion squared over g. If you can identify subpopulations, say by their kinematics and half-light radii, you could apply this mass estimator using 2 different half-light radii, 2 different characteristic velocity dispersions. The subpopulations are in equilibrium in the same potential well, but I can get a handle on the enclosed mass at 2 points, and I can get a measure of the slope of the mass density profile. Why is this important? Just to remind you again, it's galaxy scales where you start to see the nature of dark matter. On very large scales, clusters of galaxies, the microwave background, gravity is dominating, and all dark matter. There's many different types of dark matter shown here, a plot from Ostreicher and Steinhardt 2001. At large scales, all the different dark matters agree. It's only on individual galaxies, in particular dwarfs, you see the biggest divergence in predictions of properties such as inner density profiles. If I have a few more minutes, cores and cusps indeed is a very important tension between the predictions of cold dark matter, no physical scale that could imprint, no physical property that could imprint a characteristic scale. That means the predicted density distribution for cold collisionless dark matter just steadily increases as a power law towards the center. No scale like you can see here for fuzzy dark matter. So they predict a cusp. However, if you analyze the motions of stars in the most straightforward way, you get a core in both dwarf spheroidal galaxies and gas-rich dwarf galaxies. A question is this core the intrinsic property of the dark matter, such that streaming motions, or can you redistribute dark matter such that it starts with a cusp, it is cold dark matter, somehow that cusp gets erased? These are just plots showing you that both gas-poor and gas-rich galaxies have cored present-day dark matter density profiles. But the issue is, has that been created by the gravitational interaction between dark matter and baryonic matter? So could this work, that a cusp profile be flattened? And the answer is yes, it could. If I have rapid injection of energy and momentum from short-lived massive stars, I can create a new equilibrium state which has less dense inner regions. Very influential paper, Ponzin and Governatu, little cartoon here you can look at, showing how if I have a lot of baryons in gas at the center, form stars, I can change the gravitational potential sufficiently that the equilibrium distribution puffs up. But what's important is that you need many rapid bursts of star formation. You need repeated bursts. And what that means is that in principle, you can transform, this is a plot of density profile in the inner parts versus stellar mass to halo mass. NFW cold dark matter profile has a steeply rising profile. I can change it to be close to constant density through repeated bursts of star formation, provided, this is a plot from Bullitt and Bullen-Korshin, this does work, this is seen in simulations, but only if I have enough baryons, enough star formation. Doesn't work. There's no difference between the present day mass function indicated by the purple and the primordial cold dark matter density profile for ultra faint dwarfs. So Bootes 1, having lots of dark matter, but very low baryon content, small spread in star formation history, small spread in ages, is an ideal test bed of this idea. And it's a target of the Galactic Archaeology Survey with the Subaru Prime Focus spectrograph. We want to determine the mass profile, probably by finding subpopulations constraining the interior mass at different radii. If it has a core, then that means dark matter has a preferred scale. Just to run through this, here's the PFS pointings for Bootes 1. This is the half-light radius on the sky and nominal tidal radius. We're going to cover the whole face of it with many pointings, each with 2,500 fibers. medium resolution spectra, we'll get good line of sight velocities, good abundances, find subpopulations. Here's a different version of that plot showing the forecast for the error bars that we'll get for Bootes 1, where we find subpopulations, and for the other more luminous galaxies of our sample. These are selected to have a range of star formation histories. So we'll be able to distinguish cold dark matter predictions from baryon, changing the profile, and also other more exotic forms of dark matter. So we actually know that Bootes 1 does have members. You might say, why are you spending time to go out there? Again, Carrie Filion has identified blue horizontal branch stars that are Gaia proper motion, apparent magnitude consistent with members. So we're really going to map the full extent of the dark matter. So let me just concluding remarks. I hope I've convinced you that small things can have big impacts. We can figure out the IMF at high redshift. We can perhaps figure out the nature of dark matter. And that's one of the most important unanswered questions. We get unique insights from astrophysics, very complementary to direct searches. To the graduate students and undergraduates, stay open-minded during your career, stay interested in many problems, and perhaps get involved in PFF galactic archaeology science. Send me an email if you'd like to understand more about that. Thank you.
Thank you, Rosie. Do we have questions from the audience first? Wyse?
I have a question.
Can you come closer to the camera? Because
Hi, Rosie.
Hi.
Thais Stark-Bergman here.
Oh, hello. Hi.
Hello,
Hi,
how are you? Yeah.
Fine.
I have not such related question to dark matter, but I wonder if these dwarf galaxies have to do with in the beginning of the universe, these dwarf galaxies that are being argued to be the reionization sources of the universe. Could be these dwarf galaxies that you are studying now, those dwarf galaxies that were reionizing the universe in the beginning of the universe.
Yes. So let me just go back to the age distribution back here. Yes. So it's very interesting to try and really pin down the ages of the stars in these galaxies. As you're probably aware, old metal poor stars more or less look the same, independent of whether they're even 11 billion years or even 13.6 billion years. So we would like to know, are they quenched by, did they form most of their stars before reionization? Did they continue forming stars through reionization? Are there enough of them? And do they have enough photon leakage that they could contribute to reionization? I suspect that it's the more luminous, not the ultra faint, the more luminous galaxies that would be the ones that contribute to reionization.
Okay,
but these are certainly of an age to be forming stars around that time. And it's very interesting to try and figure out what happens to star formation through reionization.
Thank you.
Yeah.
Yeah.
Hello, my name is Miriani. And my question is about the distribution of the dark matter in these galaxies. Does it follow the Navarro profile or have a different profile?
So the systems in which we have good measurements of the velocity dispersion as a function of position are shown here. Now, when we are only measuring one component of the velocity of the space velocity, which is the line of sight velocity, there is an ambiguity in how you analyze the data. So it is always possible to find a version of the Navarro-Franken-White that can fit any one particular dwarf galaxy. But what we've shown here is the analysis of the spatial distribution of the starlight and the velocity dispersion, the line of sight velocity dispersion as a function of radius for 6 dwarf spheroidals with a range of star formation histories, but we have assumed an isotropic velocity dispersion. And we find that they do not fit the NFW profile. There's a turnover as opposed to the cusp that is predicted for NFW. This work was criticized because we assumed isotropic, and there's what's referred to as an anisotropy mass degeneracy, in that in the genes equations, the equations that we used in this analysis, you can have a different mass profile if you allow the anisotropy to change as a function of radius or just be different from 0. But our argument is that these are very different dwarfs. If you allow the anisotropy to be non-zero, then you would expect it to be different for the different systems. They have different star formation histories, different orbits about the Milky Way, different total luminosities. You would not a priori expect to get the same result with the assumption of isotropic velocity dispersions. So we argued that the fact that they all gave the same result suggested that that result was valid. That's the gas poor. Gas rich is shown on the right-hand side here. For gas rich, you don't have the ambiguity back here that you're just measuring one component of a velocity dispersion. For gas rich, you actually use tracers that are in circular orbits or close to circular. How close they are is a source of some debate, but not very much. And here's gas rich. Again, this is the slope of the inner part here. Navarro-Franken-White is down here. A core is up here, and the bulk of the systems are up here, also not consistent with Navarro-Franken-White. So assuming that this is correct, it would make sense that both gas-rich and gas-poor dwarfs have similar profiles. But then that leads to the the question that, okay, people said, okay, we'll accept their core, but that's the present day dark matter distribution. And maybe it's been affected by the fact that the dark matter has baryons inside. And that's what we'd like to test. We don't actually have any mass profiles for the ultra faints yet. And that's why it's really important to include an ultra faint in the sample that we're going to get with the Subaru prime focus spectrograph. All we have at present for the ultra faints is, sorry, going back here, is this one estimate of the mass inside the half-light radius. And that's basically the analysis here. So we don't have a detailed mass profile, but that's what we want to get with all the data that we're going to get. We're at least going to be able to find subpopulations in Bootes 1, and we may even get enough stars, because we don't really know. I mean, I briefly went over that we know there's some stars out here, but we don't know how many member stars there are. And we have enough fibers that we're just going to target everything.
Okay, thank you very much.
Yeah, thanks.
Thank you. Do we have questions from the audience online? If not, I have one question. That is, in the past years, there's been lots of talk about the ultra diffuse galaxies, and some people say they're separate type of galaxy, but it seems they're just more of a continuum. So I'd like to hear your view on this topic, connecting to ultra-faint dwarfs. How similar do you think they might be in terms of dark matter, maybe?
I think that we are now discovering that there's a whole low surface brightness universe that has not yet been well explored. Some of the ultra diffuse galaxies do seem to be in clusters and plausibly have been tidally affected by the galaxy cluster environment. And how much that has contributed to the low surface brightness is still to be determined. I think the whether there's a continuum in luminosity from the ultra faint dwarfs through to the ultra diffuse dwarfs, I would say remains to be seen. I think most of them that have been discovered, I think it's still true that most of them have been discovered in, as I say, large clusters of galaxies. And they do tend to be much higher luminosity than these little dwarfs that we're talking about. But I think some similarities in how they formed, but they probably haven't had the same outflows that would be contributing to the low baryon content and plausibly the extended distribution that we see in the ultra faints. So some similarities in physical processes behind the low surface brightness, some not. I think it's a very interesting question, though. Yeah.
Thank you, Rosie. Do we have any more questions from the audience online or here? If not, let's thank Rosie again.
Okay, thank you.
So thanks a lot. I'll send you the link of the YouTube talk later.
Okay, thank you. Thanks, everyone. Bye-bye. Bye.
Pessoal, a gente vai terminar essa semana que vem. Não é para ter tão longo.